welcome Carlos Arreche from the Graduate Center of the City University of New York, and he'll give a talk on his complete algorithm to compute the Galois group of a parameterized second-order linear differential equation.
Good morning. Thank you all for being here, and thank you, Alexei, for the invitation.
Just open the door.
Hello again. Apologies. So let me begin with a simple example of the parameterized theory. So in this theory, you have one or several main derivations. So in this case, I'm thinking of ddx as being the main derivation, and you have one ddx equation where there are these other t's appearing, and you think of the t's as parameters. So this is one family of first-order linear differential equations parameters by t, and what the theory is for is to understand all the differential algebraic consequences of that original equation that we have, or system of equations. In particular, with respect to the derivations that don't appear in the defining equations, right? So it turns out that this equation 1, so any solution to this equation does have to satisfy the equations, as we'll see. Let me just observe that in this simple example, you can think of a solution of this equation very concretely as x to the t, but this is all formal and algebraic, so my fields don't consist of functions. They're just formal differential fields. So when you take the dx derivative of the logarithmic dt derivative of the solution, what you get, you just observe that it's symmetrics in ddx and ddt. So you obtain this consequence that the ddx derivative of the ddt logarithmic derivative is equal to 1 over x. So you're deducing facts about the ddt derivatives of y, even though you weren't told anything about them before. And so what the theory does in general is it allows you to carry out this kind of analysis systematically without necessarily being able to write down solutions or to know what they look like or to interpret them in terms of functions. You can just deduce all of these relations out of your original system of equations. In general, if you have an nth order linear differential equation where the coefficients belong to a particular delta field k that you care about, I'm going to think of delta as consisting of, well, the little delta that appear in the original equation, and then all the other derivations, I'm going to think of them as derivations with respect to parameters. So if you like, you can think of, these RJs, maybe delta is ddx, and the RJs depend on x as well as on some other t's, and pi consists of the derivations with respect to the t's. And the problem that you're trying to solve in general is to find all the big delta algebraic consequences of this original equation. And the way that the theory accomplishes that is by associating to this equation a differential algebraic group. I'll get to the definition shortly. It's a pi algebraic group, and it encodes all the relations that you're looking for, that you're trying to find and understand. So now I'm going to give a slightly technical definition of what's a linear differential algebraic group. For technical reasons, I'm going to make this assumption on F, I don't want to discuss this for too long, but if you haven't seen this definition before, being differentially closed is the differential analog of being algebraically closed. So what it means is that if you have any consistent or reasonable system of pi algebraic differential equations with coefficients in F, then you can solve them in F already. You don't need to take big extensions. And the reason I'm making this assumption is not necessary. It follows from work of Widmer and also Gillet, Borshinsky, and Ovshinnikov, and other people that you can carry out the theory without making this strong assumption on F, but it allows you to talk about the Galois groups as actual groups of matrices instead of group functors. So it's a little simpler to talk about. So a linear differential algebraic group is a subgroup of GLNF that's defined by pi algebraic linear differential equations. Pi algebraic equations. They don't have to be linear. So it's the differential analog of an algebraic group. So some groups are special in that their conjugate or essentially consists of groups of matrices, and these groups are defined by just algebraic equations. The derivations don't appear, except to say that every matrix entry has to be pi constant, or constant with respect to each parametric derivation. So these groups are special and are related to isomonodromy phenomena, and we'll get to that shortly, but I wanted to have the terminology now. So to have some concrete examples in mind for pi algebraic groups, if you had a differential operator in M differential indeterminate, so what I mean is there's a linear combination of higher derivations of M free variables. Any linear differential operator, sorry, I should say. So if you write down the condition that you want that operator to kill the pi logarithmic derivative of A, should have written this before, but by pi A over A, I simply mean this tuple. So it turns out that any differential algebraic subgroup of the of GL1 or the multiplicative group of F is defined by just a linear differential operator killing these logarithmic derivatives. And something similar happens with the additive group. Every differential algebraic subgroup of the additive group of F is actually defined by the vanishing of one or several linear differential operators hitting B. Okay. So these are the kinds of groups that will appear as Galois groups in the parameterized Arreche theory. So let me briefly review that. I'm going to be working over a very concrete delta field K. The theory applies more general, but let me make the definition just for this K. I'm still assuming that F is pi closed, and I'm going to extend these pi derivations to K by just demanding that every one of them kills X. Then the delta is going to denote the set of derivations consisting of pi and then the derivative with respect to X. So the parameterized Arreche theory associates a PPV field for this equation that satisfies these three conditions. If you're familiar with non-parameterized classical Arreche theory, these conditions look very similar. The only difference is that you're making a splitting field that's generated by a full F basis of solutions to the equation, but then is closed under all the derivations, both the dx as well as the parametric extra ones. So the group of delta automorphisms of this differential splitting field is by definition the parameterized Arreche group. So it's all the field automorphisms of M that leave K fixed and commute with a single derivation in delta, both the dx as well as the parametric ones. So just like in the classical Arreche theory, the action of the Galois group is determined by what it does to these generators. And that defines an embedding for you of the Galois group into GLNF. And its image is a linear differential algebraic group. So I'm going to briefly, I'm skipping a lot of algorithms here that are important, but so this parameterized recursive theory contains the non-parameterized one as a special case. If you just have an empty set of parameters, then all the definitions are just talking about standard recursive theory. So Kovacic in 1986 came up with an algorithm not to compute groups, but to compute a basis of Liouvillean solutions for the equation if it exists. It turns out that what Kovacic did is very nearly enough to compute the groups. So that's why he often gets credit for coming up with the first algorithm to compute these groups. That only worked for second order equations. What I'm skipping here is a lot of work of Singer and Ulmer, for example, to compute Galois groups in general for reductive groups. But eventually, Khrushchevsky published a complete algorithm to compute the Picard-Besser group, no parameters yet in any of these, of an arbitrary and ordered equation, always over this field of rational functions in X. More recently, Dreyfus published an algorithm that allows you to compute the parameterized Picard-Besser group, assuming both that this middle coefficient R1 from here is 0. That guarantees that the group is unimodular, and by that I just mean that it's contained in SL2. Kovacic does something similar, and the reason that they're doing that is that SL2 has less subgroups, so they're easy to compute. And then in Dreyfus' procedure, you have to make this additional assumption that either the parameterized Picard-Besser group is reductive. I won't define this in general, but concretely later. And that if it's not reductive, then you have to ask for its maximal reductive quotient to be pi constant. What we said before, that optoconjugation consists of matrices with entries that are constant with respect to every parametric derivation. Just a little later, I published an algorithm just with one parametric derivation with no restrictions.
I have a question. So, I think people thought that Dreyfus had an algorithm for any subgroup of SL2. So it's not the case.
No, you do need this condition, and I'll explain in more detail later why you have to demand that. His procedure, in fact, works, but it doesn't end if you don't make these assumptions. So you could keep trying to find more equations that aren't there.
But he does not have a complete algorithm for SL2, correct?
No, right. There's no way to tell whether you're done computing or not. Okay, and then more recently, Minchenko, Ovchinnikov, and Singer in a pair of papers published an algorithm to compute the PPV group for this equation with arbitrary order n and an arbitrary finite set of parametric derivations, still with the same restrictions that appear in Dreyfus' algorithm. And in fact, they help clarify why these restrictions come up. So what I'm going to talk about today is how to extend Dreyfus' results to remove both the assumption that this R1 is equal to 0, that the group is in SL2, and also remove the assumption on the reductive quotient being pi constant when the group is not reductive. So I'm going to start talking about how if you knew how to compute an arbitrary PPV group under this R1 is equal to 0 condition, that would allow you to reconstruct the group of any equation that you like. So I'm going to start out with a second order equation. This funny normalization is just meant to make the notation later look nicer. It's not a big deal, but all these 1/4 and 1/2. So what you do if you get an equation that doesn't have R1 being equal to 0, this is all very classical, by the way, but I want to write down concretely what the change of variables does. You can relate its solutions to the solutions of an equation like the ones that we're assuming we can solve. This formula, as you can find in Vanderpoort and Singer, for instance. So if you take a basis of solutions for this associated equation, and then from that PPV field, you're assuming that you can compute H. What you do is you adjoin a solution to this other auxiliary equation, and so you make this big PPV field that also has this little zeta in it, and what the bottom line is supposed to say is that zeta eta and zeta xi is a basis of solutions for the equation that you want originally. Okay, so this change of variables between an equation that you want to solve and one that you don't yet is given very concretely by multiplying by an exponential element, right? Something that satisfies this equation, and all of this is happening inside of this big PPV field here. There's a lot of notation here, but it gets summarized in this diagram. So just to remind you, E is the PPV field, so whose Galois group. G is the one that you're trying to compute. M by design is a PPV field whose Galois group is unimodular in SF2. The equation that M comes from has R1 equal to 0. And this M is obtained by joining this exponential that you need to go back and forth between the solutions. So the parameterized Galois correspondence takes this diagram of fields and makes it so that the Galois group of U over K is forced to be precisely this group. This notation here is this is actually a fiber product in this category. That doesn't matter very much. That's what it is. So what you're able to do is compute the Galois group of U first, and then compute G as follows. So if you look at the eta and psi, they were generating the PPV extension whose group is in SO2, unimodular. So this basis for this set of generators, excuse me, for U over K, embeds the Galois group of U over K in GL3F this way. And now zeta, eta, and zeta psi, they were a basis of solutions for the equation that you're trying to solve. And the surjection from this big PPV group into the one that you want is given very concretely by this. And so what you have to do in the end is compute the defining equations for G as a subset of D times H. D is this group that comes out of the change of variables, and H is the unimodular one. And the Kolchinov-Stropsky theorem allows you to compute exactly this intersection of fields, the group lambda, and the defining equations for G inside of this direct product. And so that's how you reduce to the unimodular case. So now what I want to discuss is how, assuming that R1 is equal to 0, what happens with the unipotent radical and why you need these assumptions on the reductive quotient being pi constant to compute it, and what to do if the assumptions aren't satisfied. So it turns out this comes from Kovacic's algorithm. When the group is not reductive, you can find very special solutions for your equation, and one of the solutions satisfies the first order equation, and then the other one satisfies this other relation. And so concretely, what I mean for second order equations, you can say exactly what the unipotent radical is. They are the matrices that have ones along the diagonal and then just a B in here. Those are the unipotent matrices, and the unipotent radical is the subgroup of all those matrices. The reductive quotient in this case is exactly this group A. So let me tell you first how to compute this reductive quotient A, or summarize how to compute it. This choice of basis for the unimodular equation has the Galois group acting on them like so. And then these two relations are formal. On the one hand, sigma transforms the parametric logarithmic derivative with respect to any partial in pi. In this way, just adds the logarithmic derivative of this a sigma coming from the action of G on eta. And it turns out that the partial logarithmic derivative of eta, if you hit that with the dx, like we saw at the very beginning in the example, that's the same as doing it the other way, and that is in k. So the way you say this usually is that partial eta over eta is a primitive over k, or an integral. And these observations allow you to reduce the computation of this V group A to solving this creative telescoping program. And there are lots of algorithms, some even very recent, to try to compute this. All the P's that satisfy a relation like that. Any P that you can find that satisfies this condition, you can show that happens precisely when that linear differential operator kills the parametric logarithmic derivatives of A. Which you'll recall from Cassidy's result, every subgroup of GM, and A is one of these, is defined by equations like that. So now, to compute the uniform radical, you make very similar arguments. You can write down concretely how sigma is acting on the solutions that you haven't adjoined yet. And these computations allow you to reduce the computation of B to solving a creative telescopic problem. So far you don't need anything, this always holds. But what happens is that when A fails to be pi constant, then this PPV extension has infinite algebraic transcendence degree over K. And when you try to find all the P's that satisfy this, you keep having to add more higher parametric derivations of the solutions involved, and then try to find relations with those. And once you're done, you add more and you add more, but you never finish. So when A is pi constant, then eta, we saw before, like taking partial of eta over eta already stays in K, so you don't need to add anything else, just eta. And that's why you can compute it when A is pi constant. When it's not pi constant, what you do is you compute, you find a vector space.
So that would be the place where Dreyfus' procedure was failed, correct?
Yes. Yeah, here you will, so he comes up with this condition here, but when you sit down and you try to find all the P's that satisfy this, you won't finish unless A is pi constant. But you can reduce to that case with this result. So if you find all the derivations in the vector space spanned by pi, all the derivations that think that A is pi constant, you can find a basis of commuting derivations for that subspace. That's my pi prime. And now, if I forget about pi prime is a set of commuting parametric derivations, and I can do everything we just did. Again, I get this pi prime algebraic group by thinking of pi prime as a new set of parameters. So with this pi prime defined like so, you can show that first of all, G prime, the reductive quotient of G prime is pi prime constant. So that means that you can compute the unipotent radical of G prime. And moreover, the defining equations for the unipotent radical of G prime are also defining equations for the unipotent radical of G, which is the one that you're trying to compute. And so this result allows you to reduce the computation of the unipotent radical of G, which is the one piece missing, to the one that you know how to do already when the reductive quotient is pi constant. Thank you for your attention.
Questions?
Is this algorithm implemented, or is it far from an implementation?
No, it shouldn't be very far. I'm working on it at the moment.